Hello, this is Richard Hammack's Calculus 1 course. We are in part 3 of the course on derivatives. Today is lecture 21, derivatives of trig functions. Before getting down to business, let's take a summary of what we know so far. Remember that the derivative of a function f of x is another function called f prime of x, defined as f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Also equal to the limit as z approaches x, f of z minus f of x over z minus x. And this equals the slope of the tangent line to the graph of y equals f of x at x. So if you take a function y equals f of x, pick out an x value, look at the tangent line to the graph of f of x at that point, the slope m of that tangent line will be f prime of x. F prime of x is also denoted as y prime, or dy dx, or ddx f of x. And lately we've been concerned with the business of finding rules for computing derivatives of functions bypassing the limit process. And as long as our function has a form that a rule applies to, we can find its derivative very quickly. For example, the derivative of a constant is 0. The derivative of x is 1. Then there's the power rule that says the derivative of x to the power of n is n times x to the power of n minus 1. The derivative of e to the x equals e to the x. We had a constant multiple rule. The derivative of c times f of x is c times the derivative of f. The sum difference rule tells us that the derivative of the sum or difference of a sequence of functions is equal to the sum or difference of the corresponding derivatives of those functions. And then in our last lecture, we developed two new rules: the product rule that says the derivative of f of x times g of x is f prime of x g of x plus f of x g prime of x, and the quotient rule, ddx of f of x over g of x, is f prime of x g of x minus f of x g prime of x over g of x squared. So this is our list of rules so far. Our purpose today is easy to describe. We're going to deduce 6 new rules, one for each trigonometric function. We'll find the derivatives of all 6 trig functions. Let's get started. We're going to need some tools from the toolbox, and I'll remind you of these. First of all, way back in part 2 of the course, we talked about limits of trig functions, and this was an important limit, we said. The limit as h goes to 0 of sine of h over h equals 1. We looked at many examples of that, and we said that we would need it later in the course, and today is the day we're going to need it. Another limit from part 2 of the course that we took note of that we'll use today is the limit as h approaches 0 of cosine h minus 1 over h equals 0. So we'll need these two limits today. We'll also need a few trig identities: the sum formula for sine of alpha plus beta equals sine of alpha cosine beta plus sine of beta cosine alpha. Also the sum formula for cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. And we made note of these identities way back in part 1 of the course. And we said we'd need them at some point, and today we'll need them. And one other identity we'll need today that should be fresh in your mind: sine squared x plus cosine squared x equals 1 for any value of x. So as we go through today's business, we'll have to reach into the toolbox here and pick out the appropriate tool. Now, our business is to find derivatives of trig functions. Let's start with the derivative of sine of x. We're going to work this out using the limit definition of sine, and we'll come up with an answer which is going to be a new rule. And after you've learned that rule, you never have to work out the limit again. Let's see what we get. The derivative of sine of x would be, well, we have to use the limit definition of the derivative with the function being sine instead of f. The derivative of sine of x is the limit as h goes to 0 of sine of x plus h minus sine of x over h. Now, when looking at this limit, the denominator is going to 0, so you're hoping to somehow dispose of that denominator in some legitimate way. Usually in a limit, you try to factor out an h from the top to cancel with this one, but there's no way we could factor out an h from the signs. So we have to be a little more clever. What we're going to do here is use the sum formula for sine, right here with sine of x plus h. So letting alpha be x and beta be h, sine of x plus h right here becomes sine of x cosine of h plus sine of h cosine of x with this formula. And then we have minus the sine of x right there. Okay, what can we do here? We want to get rid of this h. And look what we have right there, a sine of h over h. And we know the limit as h goes to 0 of sine of h over h is 1. So that's a pattern that we could use there. We got a bunch of other stuff too. Let's see, a sine of x times a cosine of h, and also a minus sine of x over here. Look at the first and last terms. They both have a sine of x. So let's factor a sine of x out of them and see what we get. The sine of x times the cosine of h minus the sine of x. If you factor a sine of x out of those terms, you get sine of x times cosine h minus 1. And then these middle terms, we'll scoot those over to the other side. Sine of h times cosine of x. We'll put it right there. Okay, let's see what we have. Look at this, a cosine h minus 1 over h. And we've got this limit, and also a sine of h over h, matching this limit. So let's break up this sum in the fraction as two separate fractions, both over h, and write the first part as sine of x times cosine h minus 1 over h, right there, and the second part as sine of h over h times the cosine of x. So now we can see that as h goes to 0, this cosine h minus 1 over h, according to this limit, becomes 0, and the sine of h over h, according to this limit, becomes 1. So applying limit laws here, bringing the limit into the parentheses, we get sine of x times 0 plus 1 times cosine of x. And that's equal to cosine of x. So this is our latest new rule. We've just figured out that the derivative of sine of x equals cosine of x. Let's tally that. It's a new rule. The derivative of sine of x equals cosine of x. And commit that to memory. Let's think about what this new rule is saying geometrically. Here's the graph of y equals sine of x. And we just figured out that the derivative of sine of x is cosine of x. And let me plot this derivative cosine of x in blue. And I want to point out that this really makes sense when you think about it. For example, look at the graph of sine of x and at the points at which the tangent line has slope 0. At pi over 2, at 3 pi over 2, at 5 pi over 2, at negative pi over 2. Sine of x has slope 0 at all of those points, and that's exactly where cosine of x is equal to 0. Cosine of x is giving slopes of the graph of sine of x. Right here, it looks like sine of x has a slope of 1. And look, cosine of x is 1. Right here, sine of this 2 pi is 1, and that seems to match the slope of the tangent line. At pi, the slope of the tangent to sine of x looks like it's about negative 1, and cosine of pi is negative 1. So when you look at it from this point of view, it makes perfect sense that the derivative of sine of x is going to be cosine of x. Cosine of x matches what you would expect to get for the derivative of sine of x. Let's now move on to the derivative of cosine of x. And in fact, let's think geometrically here, reasoning from the graph and see if we can guess what the derivative would be. Here's the graph of our function, cosine of x. And from what we did before, you might guess that the derivative of cosine x is going to be sine of x. Let's see if that makes sense. Well, look at where the slope to cosine of x is 0. At x equals 0, x equals pi, x equals 2 pi, and sine of x is certainly 0 at those values. So that looks good. However, as we move on from x equals 0 towards pi over 2, notice that the slopes to cosine of x are negative, whereas sine of x is positive. And in fact, at x equals pi over 2, it looks like the slope to cosine x is negative 1, but sine of pi over 2 is positive 1. So for this reason, you might guess that the derivative of cosine of x is not sine of x, but negative sine of x. That seems to match. And in fact, look at, say, 3 pi over 2. The slope to cosine of x looks like it's positive 1, and negative sine of 3 pi over 2 is positive 1. So just looking strictly at the graphs, it looks like the derivative of cosine of x is likely to be minus sine of x. And in fact, that does turn out to be true, and you can show it. To check that, take the derivative of cosine of x, use the limit definition of the derivative. Limit as h goes to 0 of cosine of x plus h minus cosine of x over h. And then you have to use the sum formula for cosine. Cosine of x plus h is cosine x, cosine h, minus sine x, sine h from our toolbox, and then minus the cosine of x. And I'm not going to do everything in this limit. I'm not going to dot every I and cross every T, but I just want to point out that what we're getting here, if you look at the sine of h over h, that's multiplied by a minus sine of x, that's going to turn into negative sine of x. And also here you have cosine x, cosine h, minus cosine x. Factor out a cosine x from those terms, you get cosine x times cosine h minus 1 over h. All of that turns to 0 in the limit if you reach into our toolbox and take out the appropriate limits. So I'll skip the details of that, and you can check that yourself. You do get negative sine of x. So either take it on faith that this is what you get, or check these details, or read it in the text. The derivative of cosine of x, as indicated here, and also in this picture, does turn out to be minus sine of x. So we've got two new rules so far. The derivative of sine of x is cosine of x, and the derivative of cosine x is minus sine of x. So we're a third done. Remember, we wanted 6 new rules, 1 for each trig function. Let's start working on those other 4 trig functions. Think about the derivative of tangent of x. And what we'll do here is we're going to work out the derivative, we'll get a rule, and we'll commit the rule to memory. The derivative of tangent of x would be the derivative of sine x over cosine x, since tangent equals sine x over cosine of x. And notice here we're not going to need a limit because we're taking the derivative of a quotient. We can use our new quotient rule from our previous lecture. The derivative of sine x over cosine x by the quotient rule is the derivative of the top function sine of x times the bottom function cosine of x minus top function times derivative of bottom divided by the bottom function squared. That would be a cosine squared x. Now the derivative of sine of x that happens right here, we know that's cosine of x, and then this derivative of cosine x that's right here, we now know that's negative sine of x. So let's take those derivatives. We get a fraction cosine x times cosine x minus sine of x times minus sine of x all over cosine squared x. So on the numerator, that's cosine squared x plus sine squared x, and that's divided by cosine squared x. But remember from our toolbox today, we have an identity, cosine squared x plus sine squared x is 1. So this is nice. This simplifies to 1 over cosine squared x, which you could write, if you liked, as 1 over cosine of x squared. And why would we do that? Well, 1 over cosine x is secant x. So we get as our final answer, the derivative of tangent of x is secant squared x. So this is our latest rule. It's our third new rule today. The derivative of tangent of x is secant squared x. Commit that to memory. If you ever do forget it, you can actually work it out as you did here pretty quickly, but it's probably best to commit it to memory, and you'll get to the point where you use this enough that it'll be natural that you remember it. Moving on to our next rule, we need a formula for the derivative of secant of x. Now, secant is 1 over cosine, so we're looking for the derivative of 1 over cosine of x, and again, we can use the quotient rule. We'd get the derivative of the top function 1 times the bottom function cosine of x minus the top function 1 times the derivative of cosine of x all over cosine of x squared. Now the derivative of 1 is 0, so this first term here drops out, and we're left with negative the derivative of cosine of x, or negative sine of x, negative sine of x over cosine squared x. Now let's take this expression, which is sine of x over cosine squared x, and write that as 1 over cosine of x times sine of x over cosine of x, and then you see that we're getting secant of x times tangent of x. So this is our new rule. The derivative of secant of x is secant x tangent x. Let's record what we've just found on this slide. 2 new rules. The derivative of tangent of x is secant squared x, and the derivative of secant x equals secant x tangent x. So we're getting our new rules quickly. Let me summarize what we have so far. The derivative of sine of x is cosine of x. The derivative of cosine of x is minus sine of x. We just figured out the derivative of tangent of x is secant squared x. And the derivative of secant x is secant x tangent x. So that leaves us with two formulas that remain to be deduced. Derivative of cotangent of x, that should be easy now from what we've done before. The derivative of cotangent of x would be the derivative of cosine x over sine of x. And here you could use the quotient rule just as we did before. But I'll tell you what, I'll leave the details to you. Maybe pause the video and work it out yourself. You will get minus cosecant squared x. This works very much like the derivative of tangent x that we just did. Just a few details are different. But check it. A new rule, the derivative of cotangent of x is minus cosecant squared x. For the final rule, the derivative of cosecant x, cosecant is 1 over sine of x, so again you can use the quotient rule, and again I'll leave the details to you. It works very similar to what we did on the previous page. You will find that you get negative cosecant x cotangent x. So that goes here. So at this point, we have 6 new trig function derivative rules. Up to this last one, the derivative of cosecant x is minus cosecant x cotangent x. So commit these rules to memory. You'll use them often in this course. Use whatever mnemonics you have available to you to remember them. A couple of patterns here. Notice that for the derivatives of the cofunctions, cosine, cotangent, cosecant, they all have a negative in front of them, whereas these all have a positive in front of them. But whatever mnemonic you use it. If it works for you, use it. Let's move on to looking at some examples that use our new rules. For our first example, think of f of x equals x cubed plus x cosine x. So that's a function. And imagine finding its derivative. Well, we differentiate the x cubed to get 3x squared, and then we'd have to take the derivative of x cosine x. And there we'd have to use the product rule, the derivative of a product, x times cosine x. So in the product rule, you take the derivative of the x, which is 1, times the second function cosine x, plus the first function x, times the derivative of cosine x, which we know from our new rule, is minus sine of x. So our answer is 3x squared plus cosine of x minus x sine of x. For another example, take the derivative of sine of x over x. Now sometimes I'll have students who have the impulse to say this is 1 because the limit is x goes to 0 of sine x over x equals 1. But we're not taking that limit here. We're taking the derivative of this function, sine x over x. And to do that, we need the quotient rule. In the quotient rule, you take the derivative of the top function, which is cosine of x, times the bottom function x, minus the top function sine of x, times the derivative of the bottom function, which is the derivative of x, 1, all divided by the bottom function squared. So there we go. Cleaning that up a little bit, our answer is, our derivative is x cosine x minus sine x all over x squared. Here's another one. Think about the function f of u equals sine squared u. And imagine you want to compute the derivative of that. Well, sine squared u, we have a rule for the derivative of sine of x, or sine of u, but not sine squared u. So maybe we can get some traction from writing the sine squared of u as sine of u times sine of u. So now when we take the derivative, that's the derivative of a product, so we're going to use the product rule. And the product rule says take the derivative of the first function, d du of sine of u, times the second function, sine of u, plus the other way around, the first function, sine of u, times the derivative of the second function, that's d du of sine of u. Now by our latest rule up here, the derivative of sine of u would be cosine of u. So we get cosine of u times sine of u plus sine of u times cosine of u. And that's 2 cosine u sine u. So of course, as you see on this page, when you're finding derivatives, you're using your rules in combination and conjunction. We're using these new rules here, but also the power rule, the quotient rule, the product rule, and so on. As you know, that's normal. Here's another example. We want the derivative of the function x squared plus e to the x tangent x over square root of x. Okay, so that's the sum of two functions. So our first rule that we're going to apply is the sum difference rule. This derivative would be the derivative of x squared plus the derivative of this quotient. And the derivative of x squared is 2x. And for the derivative of the quotient, we need to use the quotient rule. So the quotient rule is right here. It says take the derivative of your top function, e to the x tangent of x, times your bottom function, which is the square root of x, minus your top function, e to the x tangent of x, times the derivative of your bottom function, square root of x, all over the bottom function squared. So that's our first step. We've applied the sum difference rule and the power rule right here, and we've set up the quotient rule. But we have to keep going because there's still derivatives to take in applying the quotient rule. Now a little bit of cleanup here. The square root of x squared on the bottom, that's an x. And we got to do the derivative of the square root of x. So let's write that as x to the 1/2. So we're primed to use the power rule there. And let's keep working with this. So we have our 2x. And now we have the derivative of e to the x tangent of x right there. And look at that. That's a product. So for that derivative, we're going to have to use the product rule. Notice we're inside the quotient rule here. But in this step, we have to use the product rule to find that derivative. So let's do this step by step. We got the 2x, a big fraction over x. The derivative of e to the x tangent of x by the product rule is the derivative of e to the x, which is e to the x, times the second function tangent of x, plus the first function, e to the x, times the derivative of that second function, tangent of x. And the derivative of tangent of x, we know from our new rule, is secant squared x. So all of that is this derivative, and it's multiplied by the square root of x. And then we have minus e to the x tangent of x times the derivative of x to the 1/2, and we could get that derivative with the power rule, 1/2 x to the power of minus 1/2. So at this point, we've taken all the derivatives, and if this were a test question, it's a perfectly fine answer. You may want to do a little cleanup here, bring that negative power down to the bottom as an x to the 1/2, and that's the square root of x. And if you wanted to, you could further clean this up by breaking up this into a fraction. And you got a square root of x over an x. That's a square root of x at the bottom. And consolidate this. So this is all cosmetic at this point. We had our derivative right here. We've simplified a little bit. So let's call this our final answer. So notice in this problem, we had to use a lot of different rules. And when we used the quotient rule, in applying it, we had to then use the product rule. And that's pretty typical. And obviously, you want to work enough of these examples so that you're good at that. And you see it coming, and you know how to handle it. For our next example, let's find the equation of the tangent line to the graph of y equals sine of x at the point 2 pi over 3 sine of 2 pi over 3. In degrees, 2 pi over 3 is 120 degrees. So sine of that, if you think about the unit circle, is square root of 3 over 2. So we're looking at the point on the graph of y equals sine of x right here at 2 pi over 3 for x. So here's our point on the graph, 2 pi over 3 comma square root of 3 over 2. Sketching in that tangent line in red, it looks something like this. So we are looking for the equation for that tangent line, not just its slope, but its equation, y equals mx plus b. We have a point on the tangent line, so that's good. In order to find the equation y equals mx plus b for this tangent line, we need its slope m. Now, of course, the slope of a tangent to the graph of y equals sine of x at a point x sine of x is given by the derivative dy dx, which we now know by our new rule is cosine of x. The derivative of sine of x is cosine of x. So this cosine of x gives us the slope of any tangent line at any given point x. We are interested in what happens at this explicit point right there, 2 pi over 3 for x. We are interested in the slope of the tangent line to the graph of y equals sine of x at the point x equals 2 pi over 3, y equals square root of 3 over 2. So that's the derivative dy dx evaluated at x equals 2 pi over 3. In other words, it's cosine of 2 pi over 3. That's cosine of 120 degrees. If you think about the unit circle, that's negative 1/2. So that tells us that the slope of this tangent line is negative 1/2, which certainly looks reasonable. Rise over run it's definitely negative, and it looks like for a run of 2, you go down 1. So that's entirely what we would expect. This computation tells us that the slope is exactly negative 1/2. Okay, so we can put this together now. We want the equation of this tangent line. Let's use the point slope formula for the equation of the tangent line. The point slope formula is y minus y naught equals m times x minus x naught. Plugging in our data, y naught is the square root of 3 over 2, m is negative 1/2, and the x naught, that's this x value of our point, it's 2 pi over 3. We put that right there, and at this point it's just cleaning up. We can distribute the negative 1/2 into the parentheses and add a square root of 3 over 2 to both sides. And here is our equation. Y equals negative 1/2 x plus pi over 3 plus the square root of 3 over 2. That's mx, where m is negative 1/2, plus b, where all of this is our b. That would be our y-intercept, so pi over 3 plus square root of 3 over 2. That's right there, that number, where that red line hits the y-axis. So there's our equation. That's it for today. The big takeaway is we have 6 new rules. Get some practice with these. In our next lecture, we'll take a pause and not talk about any new rules, but instead talk about a topic called higher derivatives, which is taking derivatives of derivatives. And after we do that, we'll move on to more rules. So I'll see you next time in higher derivatives. Goodbye.